So, okay, let's unpack this. If you take away your hands and your feet, you actually lose more than half the bones in your entire body.
Yeah, which is, I mean, it's just wild to think about when you put it like that.
Right. It's exactly 106 bones specifically. You've got 54 in the hands and 52 in the feet out of the standard 206 we all learn about.
And that's over 50% of our total skeletal complexity packed into, just a tiny fraction of our physical mass.
Exactly. We basically trade bone size for this insane mechanical resolution just so we can thread a needle or, like, palm a basketball.
Yeah, or strike a flint. Historically speaking, it's an incredible trade-off.
So welcome to today's deep dive, everyone. We are digging into some fascinating evolutionary biology notes and anatomical research today.
But we're really going to completely change how you think about your own body.
Yeah, because our mission today is to completely dismantle the idea that your skeleton is just, one single fixed architectural blueprint.
It's definitely not. We're
Nah.
looking specifically at the appendicular skeleton today.
Which is your limbs and the girdles that anchor them to your core. So we're talking arms, legs, shoulders, hips.
Right, the stuff that hangs off the main frame. The word itself actually comes from the Latin word appendere.
Which means to hang upon, right?
Exactly. It defines it in direct contrast to that central load-bearing axis, your skull, your ribs, your spine.
Right, the axial skeleton.
Mm.
So the conceptual split between that central core and the hanging appendages, I mean, it feels like common sense to us now.
Sure, yeah, you look at a person and you see a torso and some limbs.
But the thing is, it wasn't always the standard way anatomists mapped the body. Like, how did they actually decide where to draw this line?
Well, it's interesting because the axial and appendicular split isn't like a physical law of nature. It's actually a naming convention that was born from 19th century comparative anatomy.
Oh, really? So older scientists didn't use it?
No, not at all. If you look at early pioneers, like Andreas Vesalius back in 1543, they just organized bones by body region.
Oh, I see. So, like, if a bone was in the chest area, it was just a chest bone.
Exactly. Geography was everything. The split we use today only really sharpened when scientists started asking, why limbs actually exist in the first place.
Right, asking the evolutionary questions.
Yeah, and that brings us to Richard Owen in the 1840s. He's the guy who actually coined the word dinosaur in 1842.
Oh, wow. Good trivia there.
Right. But in 1849, he started arguing for this concept of homology. He noticed that a bat's wing, a whale's flipper, and your arm, they are all variations of just one underlying skeletal archetype.
Okay, wait, hold on. So the person who named the dinosaurs is basically the reason we classify our arm bones this way.
Pretty much.
Are you saying my arm is classified differently from my spine simply because it's an evolutionary variation of, like, a fish fin?
Well, yes. And it was Carl Gegenbar a bit later who actually did that math, tracing tetrapod limbs directly back to fish fins.
That is insane.
Yeah, he proved limbs are this highly specialized evolutionary offshoot. They're an add-on module.
Okay, what's fascinating here is how that completely messes with our intuition about our own bodies. Because geography doesn't match the taxonomy at all.
No, it really doesn't.
Like, proximity to the torso absolutely does not mean a bone is axial.
Right, that's a huge misconception.
Yeah.
People think if it touches the core, it's axial.
But the scapula, your shoulder blade, and your hip bones, they are sitting right there on your trunk, but they are appendicular.
Because of their function. They only exist to interact with the limbs.
Right, and then you have the weird tension where the sternum, your breastbone, is axial, but the clavicle, which physically touches it, is appendicular.
Yeah, the clavicle is an appendicular strut, but it anchors to an axial cage. They touch, but they belong to totally different evolutionary families.
And the fuzzy edges are just everywhere. Like the pelvic girdle, it's classified as appendicular.
Yes, it anchors the legs.
But functionally, it operates exactly like the axis. It is a massive load-bearing structure. It transfers the entire weight of your upper body.
It does. It bridges the two systems, but it stays in the appendicular category because of its origin.
And then on the flip side, you have the tiny hyoid bone in your neck.
Oh, I love the hyoid.
It literally floats. It is completely unattached to any other bone in your body, just sitting in muscle.
Right.
But it's considered axial?
Right, because evolutionary-wise, it stems from the same structures as the skull.
It's just so wild. But this evolutionary perspective, seeing the limbs and the girdles as these specialized add-ons, it perfectly explains the, frankly, deeply flawed biomechanical trade-offs our bodies make every single day.
Oh, absolutely. The grand trade-off of mobility versus stability.
Yeah, because the appendicular skeleton exists to enable powerful movement, right? To let us interact with the world.
Right.
And to do that, the two girdles, the shoulders and the hips, they basically make the exact opposite design choices.
They really do.
So is it fair to use an analogy here? Is the pectoral girdle, the shoulder, kind of like a golf ball sitting on a flat tee, built for maximum swing and mobility?
Yes, that is a perfect way to visualize it.
While the pelvic girdle, the hips, is more like a heavy-duty trailer hitch, built just to carry a massive load with rigid stability.
Exactly. The pectoral girdle sacrifices almost all of its structural stability for range of motion.
Because it just floats, right?
Yeah, the scapula literally floats on a cushion of muscle. The clavicle is its only bony strut connecting it to the sternum.
Which means the shoulder joint itself, the glenohumeral joint, is incredibly shallow.
So shallow. It's the most mobile joint in the human body, but because of that, it is by far the most commonly dislocated.
And that single strut, the clavicle, it pays the price for all that mobility, too.
Oh, yeah.
It's the most frequently fractured bone in the body. I mean, from newborns getting stuck during delivery to athletes just falling on an outstretched hand.
Because all that kinetic force travels up the arm, bypasses the floating shoulder blade, and just snaps that rigid little collarbone.
Right. But then you look at the pelvic girdle and it goes the totally opposite route. It sacrifices mobility for rigid stability.
Completely. The two hip bones fuse absolutely solidly to the axial sacrum at the base of the spine.
Right. So it's a deep ball and socket joint.
Exactly. It's built to securely bear the weight of the entire upper body against gravity.
But the clinical reality of that is when it fails, it's really bad, like hip fractures.
Yeah, hip fractures are devastating, especially for the elderly.
Because where the appendicular femur meets the pelvis, that bone is highly susceptible to osteoporosis, right?
Yes. Osteoporosis actually thins out appendicular trabecular bone much faster than the denser axial bones. So that critical trailer hitch just snaps.
It's a huge clinical issue. And on top of that, the functional demands on the pelvis make it a huge deal in anthropology, too.
Oh, definitely. Forensic anthropologists use the pelvic girdle constantly to estimate sex because it has to be wider for childbirth.
Right, which creates a conflict with bipedal walking, and that brings up the fossil record, the case of Lucy.
Yes, the famous Australopithecus afarensis skeleton discovered back in 1974.
She's, what, 3.2 million years old?
Around there, yeah. And her skeleton is so important because she had a decidedly bowl-shaped pelvis, just like ours.
Which proved she walked upright.
Right, but she still had very long, ape-like arms for climbing trees.
Which totally broke the assumption that upright walking and human-like arms and legs all evolved together as a single package.
Exactly. It proved that the appendicular skeleton is modular. The legs can evolve bipedalism before the arms even bother catching up.
Well, speaking of things not arriving as a single package, we need to talk about how these bones develop in a single human lifetime. Because, honestly, here's where it gets really interesting.
Oh, the bone math.
Yes, because this completely shatters the textbook rule that we have 126 appendicular bones.
It is a total illusion.
But wait, if a medical textbook says you have 206 bones total, how can that be debatable? Shouldn't counting the bones in a healthy human body be literally the absolute most basic math in all of science?
You would think so. But that 126 appendicular count is just a modal figure. It's just the most common textbook average.
So what's the actual number?
Well, real skeletons vary wildly. A healthy person could have anywhere from roughly 200 to over 213 bones.
Wow, just from normal variation.
Yep. And it's almost entirely due to something called sesamoid bones.
Okay, what are sesamoid bones?
They are small bones that literally grow embedded within your tendons in response to mechanical friction.
Wait, really? The body just makes extra bones if a tendon is rubbing too much.
Exactly. It's the body's way of building a little localized pulley system to protect the tendon from wear and tear.
So if you use your hands heavily, you might just grow an extra bone in your thumb.
Pretty much, yeah. But the craziest part is the patella, your kneecap.
Right, the kneecap.
The patella is actually the body's largest sesamoid bone.
No way. It's not a normal bone.
Nope. It develops completely inside the quadriceps tendon. Here's the kicker. You weren't even born with it.
Wait, babies don't have kneecaps?
They do not. It's just cartilage and tendon when you're born. It doesn't even begin ossifying turning into real solid bone, until a kid is roughly 3 to 5 years old.
That is mind-blowing. I had no idea my kneecaps were just giant friction pulleys I grew as a toddler.
Yeah, it completely changes how you view the skeleton. It's not just a static frame.
Right, and it's not just the kneecaps. The developmental quirks of the appendicular skeleton are so strange, like how the bones actually form.
Right, endochondral versus intramembranous ossification.
Yeah, so most appendicular bones form through endochondral ossification, right, where they start as cartilage and slowly get replaced by bone.
Exactly. It's a slow transition.
But the clavicle, our favorite fragile strut, it bypasses the cartilage phase completely. It uses intramembranous ossification, turning directly from connective tissue into bone.
Because it evolved from the dermal armor of ancient fish.
Yeah.
It's basically skin bone that migrated inside.
Which is just so cool. And because of that, it starts forming earlier than any other bone in a fetus, but it is the absolute last bone in the human body to finish growing.
Yeah, it often doesn't fully fuse until you're around 25 years old.
It's just such a messy process. And all this messiness really highlights this clinical versus anatomical debate.
Oh, big time.
Because working orthopedic surgeons and physical therapists, they often just ignore this whole axial versus appendicular split entirely, don't they?
They have to. They treat the body functionally. They use terms like upper extremity and lower extremity.
Because if someone has a shoulder impingement, you can't just treat the appendicular arm. You have to look at the axial rib cage and spine, too.
Exactly. You can't reach your arm up if your upper spine is hunched forward. The kinetic chains overlap completely. There's a huge tension between an anatomist's clean taxonomy and a doctor's messy functional reality.
Well, if we connect this to the bigger picture, this incredible flexibility, extra bones growing in tendons, bones appearing late, it perfectly mirrors how flexible the appendicular skeleton has been across deep evolutionary time.
Yeah, it really is best understood as an evolutionary module. It's a toolkit that nature can literally bolt on, heavily modify, or just completely discard, totally independent of the axial core.
Right, and you can see that in the fossil record, like gaining the module look at Tiktaalik rosé.
Oh, what a great fossil.
Discovered back in 2004, right. It's 375 million years old. And it's this perfect transitional fossil.
Yeah, it had a fish-like body, but its fins had proto-wrist bones.
Exactly. It had a mobile joint inside a fin. It's the exact structural bridge between an aquatic fin and a terrestrial limb, bolted right on to let it push up out of the mud.
Nature was just testing out the appendicular toolkit.
But then evolution is just as good at losing the module when it doesn't need it?
No, definitely. And this is a huge misconception. People think animals without visible limbs completely lack an appendicular skeleton.
Right, like whales or snakes.
Exactly. Whales are totally aquatic, but they actually have tiny vestigial pelvic and femur bones.
Just floating inside them.
Yes. Completely disconnected from the spine, just floating deep in their body wall muscle.
Wow. But if they don't use them to walk, what are they doing?
They've been repurposed. They're now used exclusively to anchor reproductive muscles.
So they didn't erase the appendicular skeleton, they just severely reduced it and gave it a new job.
Right, and you see it in snakes, too. Pythons and boas have tiny vestigial pelvic girdles.
Really? Snakes have hips.
Yes, and they have these little external anal spurs that are actually highly modified remnants of hind limbs. They use them for tactile stimulation during courtship.
That is wild. The ghosts of legs being used for mating.
Evolution never wastes raw material.
So what does this all mean for you listening at home? Basically, the appendicular skeleton is your body's interactive toolkit.
Absolutely.
It's the 126 or so bones that hang off your axis, totally dominated by that incredible density of bones in your hands and feet.
Right, every time you type an email or walk up a flight of stairs or, marvel at a whale in the ocean, you are witnessing this deeply modular, highly adaptable design in action.
It is an evolutionary marvel of trade-offs. The crazy mobility of your fragile shoulders weighed against the rigid stability of your load-bearing hips.
It's a system constantly in dialogue with the forces around it.
And understanding those forces leaves us with a really provocative thought to ponder based on everything we dug into today.
Oh, I like where this is going.
Because we know the pelvic girdle sacrificed mobility purely to bear the weight of our upper bodies against Earth's gravity.
Right. Gravity's the only reason it's so rigid.
And we also know from whales and pythons that when an environment changes and limbs aren't needed for locomotion anymore, evolution aggressively reduces that module into floating vestiges.
It strips it away.
So what happens to the human appendicular skeleton if we actually become a multiplanetary species?
Oh, wow.
Think about it. If humans spend thousands of generations living in zero-gravity space stations where load-bearing stability is completely useless, what happens? Will our distant descendants slowly lose their pelvic girdles entirely?
Because the mechanical stress is just gone.
Exactly. Could we become a new branch of spacefaring tetrapods with a totally redefined floating skeleton? It's something to chew on the next time you look at a plastic skeleton in a science classroom. It isn't a finished product, it's just a snapshot of a toolkit in motion.
What a cool way to look at it.
Thanks for joining us on this deep dive. Keep asking questions, and we'll catch you next time.